Hey, who's all here? We are about to start. Let's re-wake up Mubot. Mubot looking at all the links, getting everything ready to go. There we go. Got Mubot back awake. If you're in the chat, feel free to say hi. We're going to do some activity here. Get the notes open for today. Here we go. Taking out the data. Hey, Noah, what's up? Also, Kayla, good to see you here. Believe it or not, I ate a granola bar. Noah isn't at home. How's it go? I don't know. Hopefully there's some Seinfeld fans in the chat. Believe it or not, I'm here. I don't know if you're referencing that, Noah, but no, Kayla, you and Mr. Stevens. That nonsense. We can't do that here. Let's hop into the data set. I think there's a fly. No, let's do this. I'm just going to cough a whole bunch. Woo! Let's get some music going here. Time to get started, and let's do the activity. Okay, it is time for activity. Taking a timestamp. We are going to do question 1 on the activity. Ayo, Brendan, what's up? Check it out. Just so you know, what's The Rock say? It matters. It matters. I love it. So there we go. We got The Rock, new Rock already in here. It doesn't matter. It matters. He's very conflicted. He's very conflicted these days. Very conflicted. Rock, you gotta sort yourself out. I don't know. It did quite well. Thank you so much. Thanks to Brendan right there, doing a little audio editing. I'm gonna work on a little bit more, but good. I love it, and we're gonna make use of that, Brendan. Thank you so much. We're throwing another 1,000 points out of here. With that, we're going to look at the customer loyalty data set. And the customer loyalty data set has whether or not people churn, I believe. We'll find out here. So let's look at the data set. We have gender, married, income, first purchase, customer loyalty card, wallet share, customer lifetime value, total transactions, and the last transaction they did. A bunch of variables. It's not the churn data set. I was wrong. And a bunch of things right here. The fraction of the customer's purchases are similar. So all this good stuff, wallet share, all this good stuff. If we use the all possible models technique, there's that fly. How many models will there be? Now it does give us this equation that's so nice. It's very simple to do. Now you have to know how many x's there are. Now when you look at this, the way to figure out how many x's there are is to do the following. Each quantitative variable gives us how many x's. A quantitative, like a numeric or integer variable, will give us how many x's. Like I'm talking specifically about like this. Those are just quantitative, like how much was their first purchase? How much is their wallet share? How much is their customer lifetime value? Those are all quantitative. So each of the quantitatives is going to give us how many coefficients if they're added to the model. Like we have to have a coefficient that estimates the weight of it in the model, the differences between people, two individuals who differ by their first purchases by one are expected to differ in this, and we're predicting lifetime value. So this is the Y variable of interest. So we're not going to use that one. That's our Y variable of interest. But each one of these brings in how many coefficients to create estimates for how we should value them. They each bring in one coefficient. That is the Y variable. It doesn't get a coefficient. One, great job right there. Sierra, more points in the chat. Each one brings in one coefficient. Now we get into the interesting things, though. The interesting things are the factors. The factors work differently. When we include factors, remember the Y variable of interest doesn't get a coefficient. We're predicting Y. The other things are X's. So the Y variable of interest, it's going to hit the screen, does not get a coefficient. The X's do. Now, the categorical X's work differently from the quantitative X's. Try to color code it. The categorical X's can add up to how many coefficients? The categorical X's can add up to how many coefficients? Well, we have to know how many indicators they give. So if something gender has 2 levels, how many indicators does gender possibly input? Gender can input how many indicators into the model? Gender can input how many indicators? Gender has 2 levels. Well, gender, remember, is 2 levels, so 1 indicator. Married is 2 levels, so 1 indicator, because 1 goes to the reference, the other is the indicator. Income level has how many levels? No worries, Noah. Income level, it has 6 levels, which means how many indicators? So 6 levels, remember 1 becomes the reference, so how many indicators? And these are just the X's we have access to. Like we could put in these indicators. Like theoretically, hypothetically, we could include these indicators. 5 indicators. It's just, you just take 1 off the levels, and that's how many possible indicators there are. So we're just literally saying 6 levels, 5 indicators. And then the last one right here, loyalty card, has 2 levels, so 1 indicator. It's still 1, but it's a different 1 than saying 1 quantitative coefficient, because this is 1 indicator created from reference level comparison to indicator. So here we'd have 1, 2, 3, 4, 5, 10, 12. 12 possible X's. So we simply just take the equation right here, and we'll put in a little math, because if we want to figure out how many non-interaction models there are, we can just literally take and go K is 12, and that's how many non-interaction models there are. And this is almost set up properly for us to use. It's written more notation-wise, so we're going to have to make some adjustments to this by putting in the multiplies and divides, but that should be right there. Wow. Does it sound like there's a lot of models if we include interactions? If we include interactions, are there a ridiculous... Hey, what's up, Troy? Troy, 100 points. Good to see you here. So we're talking about making regression models now with 12 possible X's. And with these 12 possible X's, we could make a total of 4,096 different models. If we look at interactions, we have about a quintillion or something ridiculous, like a octillion number of models in the order of 4,000. It's pretty crazy, right? So this is the amount of non-interaction models. This is the amount of interaction models. Kind of some good test questions on knowing how many models we could possibly create. Some general mathematics. I'd put this on my cheat sheet. 2 to the k is pretty easy to memorize. I don't even have that one memorized. I just know it's a lot, and it balloons out of control very quickly. Like if you have 2 X's, that'd be 4 possible model, 8. I said 2. If you have 2, that'd be 4 possible models, and with interactions, 8. 3, it's 8 and 64, and you notice it goes up really quickly. At 4, you already have over 1,000. At 5, you have 32,000. So with 5 X's and considering interactions, there's 32,768 possible models. Pretty insane. Pretty insane. Using the reg subsets, this is what John was asking about. We're going to use reg subsets here to consider all possible models with a maximum up to 10 variables right here. Don't consider interactions, so do not consider interactions. And we're trying to predict customer lifetime value. So we need to go here and do reg subsets. Reg subsets works a lot like your y tilde x. And if you're ever wondering how to use a function, put the question mark before it, and it'll show you down here examples at the very bottom. So down here, you should see examples. They're doing it this way right here. Very similar to what we'll be doing with the y variable. They're storing into b. I store into model. So reg subsets right here, we need the y variable of interest, which is going to be customer LV for customer lifetime value. Make sure to use the capitals, which I didn't do right there. The data set is the cust loyalty data set. And then the arguments, we are doing up to 10 variables. It's Vmax or something. Got to remember right here, it is... I'm trying to remember the argument. It's NVMax, yes. Number of variables max is 10, so we're only allowing up to 10 variables in the model. It literally says it right there. And so let's run this and see what we get. Pretty quick right there. So what did this do? Like, can anyone explain? I'm using the all possible exhaustive procedure to select models. I just considered all possible combinations of the variables up to a 10 variable model. Does that make sense? So I didn't consider every single possible combination. I only allowed for there to be up to 10. It would start to, we can see what happens if we remove this. Oh, it still runs instantly quick. So we could have still ran it. It might be a good computer, who knows what. But this is only allowing up to 10 variables. And then you have to run the C models to see your models. and take a look. Here's our models. These are the models we've created, and we got to expand a little bit. Now, if you notice, what happens if I change this to like 13? Take a look. Oh, it didn't include anything. Wow. Let's bring this down to 5. There you go. There we go. Is this making sense what's going on right here? 2 seconds. Does this output make sense right here? Check it out. Does this output make sense that we have here the number of variables? I'm kind of making some changes to it to show what the output does right here. The number of variables is 5. It's included 5 terms in the model, 5 x's. And we have right here the AIC, which is how close our model is to the truth. Now I'm making some changes. It doesn't say to use 5, but this controls how many variables you are including. And then you can see the models that are within 4 AIC of the best. Our code wants us to do the 10 variables being used up to. So these are the models we are looking at, and the 10 x's in the model, up to 10 x's, I should say, because only this model has 10, this one has 9, this one has 8, respectively. The AICs are shown below, and the AIC is how close our model is to the truth. How many predictors are in the model with the lowest AIC? Who's got that, chat? Pretty easy to see. The output got a little bit wacky when I zoomed in, but the amount of predictors in the model with the lowest AIC is what? Who knows? It ranks them in order. Lowest AIC, it puts them in order. So the model with the lowest AIC has how many variables inside of it? Who knows? So we go right here to the first part of the output, and we have 8. Great job right there, Sierra. Excellent work. We have 8. Puts them in order for us. It took 8. Only certain indicator variables representing income appear in the model with the lowest AIC. In fact, what 3 levels are being combined together into the reference level? So this goes to model hierarchy right here. Remember, if we have a categorical variable, thank you, Noah and Brendan right there, appreciate it. If you have a categorical variable, such as like, this is the cost loyalty data set, and we have here income. Here's the levels of income, and take a look. Let's zoom out a little bit here. What we have right here is the income level 90,000 to infinity, 75,000 to 90, 60 to 75, 45 to 60, 30 to 45, and 0 to 30. The first one alphabetically is this, and here is this one right here. Here is this one, and here is this one. These all have indicators, so where are the other ones? Like, I don't see the other ones here. I don't see 0 to 30. I don't see 30 to 45, and we're talking about this output right here. We don't have these other ones. So there is the variable, someone makes 60 to 75, they'd be in that group. That's an indicator indicating that's their salary in that range. Another indicator is somebody makes 75 to 90, then they would get that indicator turned on. Another variable is somebody makes 90 to infinity. But then basically what right here? Basically all the other levels have gone to the where, which is what the question is asking. All the other levels, and when I mean all the others, I mean these others. All the other levels have gone to the where, because that's reported first because it does alphabetical. So all the other levels have gone to the where level. They are now part of that because we broke model hierarchy here by not including all the levels of income right here. They have gone to the reference level. So all the other levels are now part of the reference level, and hence we don't give them indicators. So if something no longer has an indicator, it becomes part exactly no other reference. So if you remove out an indicator, you still have to make predictions for it, so it becomes part of the reference level. So those have become part of the reference level. What variables do not appear in the model with the lowest AIC? Let's do this. Let's do call names. Okay. Oops, wrong thing. Okay. There's our model. Let me see if it's got all of it. Okay. So gender is there because this is the indicator. Married is not there. Income is, but it's does not keep model hierarchy because we don't have all the levels of income. First purchase is there. Loyalty card is not there. Can we say all of them? What do you mean by all of them? Not all of so it wouldn't be all of them. Well, I'm on the wrong question right here. The levels that are being combined together are the levels you can see right here. Those are being combined with reference, are now part of the reference. there are levels that are not part of the reference, because the levels that are not part of the reference are these right here. Does that make sense, Brendan, right there? These are not part of the reference. They are unique indicators. The ones that are now part of the reference. Where's that output? Do we lose it? Oh, here it is right here. These right here have become part of the reference. This is not an indicator ever. This one and this one, which are not included up here, you see how it kind of goes in order. They're not included, so they're now part of the reference. The reference level is now this, and these were added to it. These still have their own indicators right here as shown in the output. Loyalty card is going to be another. We just got that one. Wallet shares right there. Customer loyalty is what we're predicting. Total transaction and last transaction. So these are the only things, as far as I can tell, that are not included. And we could say some levels of income which broke model hierarchy, hierarchy, or something like that. Cool, good enough. And so we lost some of those levels there, some of those income levels, which broke model hierarchy. So there's kind of two variables and some levels. I put a star right here, like it's kind of like a kind of thing. It's not really, because we do have income in there. You see income right here, but we did not preserve model hierarchy for it. Not an end of the world thing, but yeah. There are two other models in the output. We'll show it a little bit better here with the C models. The output's just going to look crazy. I think it looks crazy. There it is. Here's the two other models. There are two other models in the output in the C models, and their ASCs are not much higher. That is correct. They're pretty close. This one is not within 2, though. This one is within 2, and 2 is like they're virtually identical range. Would you recommend to your boss to choose one of these instead? Why or why not? If your boss insisted on using one of these other models, could you object? What do you think? Would you object or not object? Just think about all models. You just be like, well, so if your boss said, we really want to use this model right here. You say, but it's not within 2 AIC. It's kind of close. 2 AIC is just our standard. You say, okay. Did you really like that model right there, model 3? Okay. All answers are wrong. All answers are right. Some answers are useful. There's no, I would not object. No, that's the thing. You're like, Rock would say, it doesn't matter. He might eventually tell us it matters. Yeah, it's pretty close. And someone might say, but Brian, you said 2, and I can subtract numbers, and I can tell you that the difference here is more than 2. I'd say it's kind of close. It's how stats works. It's like, it's about the same. It's not exactly the same. I mean, 2 is just an arbitrary point. What about 2.001? Like, does this mean your models are virtually identical? I mean, that's 2. And does this mean your models are not identical? Because ours telling me both of those are 2, and I can see they're not 2, but ours says it doesn't matter. Ours all about it doesn't matter. It's weird how ours doing that right there, but still. Oh, I've got my round or my digits, something. You can change it if you really want. Go here to options, digits, and then R will care a little bit more about what you enter in like that. And now, R's going to just do that anyways. Let's change our digits back, though. R, what you doing? That's not 2. Okay. So we'd say, sure, why not? It's about the same. I'd be like, I mean, if you really want, it's about the same. I mean, I think that first one's best. I'm just saying. I don't know why you want to use model 3, but sure. As long as my boss doesn't get mad at me talking like that. Fit a model that predicts customer loyalty value from the interaction between income level and the total number of transactions, and the interaction between income and last amount are the interaction terms statistically significant. Okay. So now we're fitting a model. We're using build model. I haven't used build model in a while. Build a model that predicts. Okay. I know we're just building it. So, customer lifetime value. Let me cheat and go here to attach and go to cust loyalty. There we go. And go to customer lifetime value. That attaches the vectors to the global data frame, so I don't have to worry about spelling and typos. Total transactions and the interaction between income. Is this it? It says Fit a model that predicts customer lifetime value with the interaction between income level and total number of transactions, and the interaction between income and last transaction. I think it's the interaction between income and last transaction. Should be right. Are the interaction terms statistically significant? Now, this is going to get pretty interesting because we have income in the interaction. Income all interaction in the interaction. Cool. So now when we go here, the summary is going to be a lot of output. It's going to be a pretty big output with all the interaction terms right there because it's going to interact on all the indicators, and it did preserve model hierarchy. You have to be careful right here because you can't look at these p-values. You need to look at the p-value of the drop 1 right here, which is only going to do, and we're doing F because it's quantitative, it's only going to do the p-value 4. So we actually do get one significant. One of them is super significant, hence the point of the question. Sometimes we do that. Total transaction income interaction is super duper significant, and the income last transaction p-value is not significant at all. So even though you could look at these and be like, it's not that significant. I think there's all the p-values saying some of them kind of are, but the variable as a whole is very significant. That means the interaction itself brings with it a lot of new information, where the other one, and look at how the p-values here are all kind of pretty interesting, moderate p-values towards 50%, but these are like not super p-values, but not amazingly statistically significant. But the variable as a whole is very statistically significant. So the inclusion of the variable, a model with and without the variable, this is the partial F done via the drop 1. The model with the first variable right here is important. We should include the first variable. We have reason right now to remove the second variable as it does not bring with it new information. So that would be that variable could go away. Given enough time and patience, it's possible to perform the all possible approach with all two interactions, but let's perform a search instead. So now we're going to the search procedure. Let me change question 1, all possible models. How's everyone doing all right tonight? I'm just going to blend sentences together. Is everyone doing all right? How is everyone doing? Step procedure now, which is something we covered in class today. Time for a little step procedure right here. We're going to make our naive model, and we're going to make our full model. So the command, I can't speak today, to make the naive model is to do your y variable of interest, do tilde1, and then you have to put in your data set. Y tilde x, comma data equals. But because we're doing the naive model, we put in the 1 for the variable. We're going to copy this right here, go right here and change this to full, and then we're going to change this to the dot raised to second. Now, it says, oh yeah, we're doing step on it anyways. I thought we were doing doing great. Great to hear that, Brendan. Thank you so much. Let's see right here. We are going to make our full model and our naive model. They're both made. They're stored into these objects, and it already gives us the code, but let's review the code. So when you look at this code right here, it's important to know what the code does. Something a little bit odd, right? Oh, that's good. So think of this code as parts. The way this code works right here is as follows. The first argument, oh, no worries, enjoy. I've got some, oh, that's what I should have tonight. We've got leftovers, rice and carrots leftovers, and I should make some meat for it or something, or maybe I can make tacos with that. That'd be good. Got some rice and some carrots. We should make some beans. Be good. Let's see what my wife wants. So I'm still not used to it. Maybe I got used to saying fiance, and now just when I say wife, I'm like, I mean, I'm very happy when I say it. I'm just like, my wife. So, oh yeah, the carrots last night, they were brown sugar and butter carrots. Oh man. So what I do is I put the carrots in a pot and like boil it to get them nice and soft. And then I put some butter in the pot with it. And I'm kind of crazy. I just shake up the butter. Like I put some butter in and I just like let it, and I just shake. Because I mean, it just gets it all across it. I mean, that works. And then I kind of wait for the butter to kind of like reduce or kind of, you know, mix it up a good bit here and there, but because kind of want a good little bit of sear on it. And then last but not least, because the sugar is going to, you know, go pretty quick, I just put a little bit of sugar on it. And then you just kind of get a nice little glaze to the carrots. As my wife, that's my purse. In honor of Bobby from King of the Hill. Great show. My brain's just, it's a long day. Brian's random references all day long. Okay, so the first argument right here is where we're starting with our model. This is the, oh yeah, Bobby's the best. The actress who plays him, she's awesome. So the scope is the fences of our model right here. Not of our model, but of our search procedure. So we're saying we can go as low as the naive, or we can go as high as the full model. So that's our fences right there. I don't know who that my purse. So now we're allowing for both directions. Trace 0 doesn't show us what's happening. What fun is that? We prefer trace on so we can watch it. So when you put trace on, you get to see what happens. You don't knit with trace on. Whatever you do, it'll cause tons of output on your screen. The way the search procedure works is we started here with the naive model with nothing in it. It then told us we should add in total transactions because that's going to lower the AIC the most. It makes every model right here and looks what's the best thing to put in. Do we not have interactions on? Because I don't see interactions. Is it preserve model hierarchy? Wait, why do we not have interactions? Let me rerun this. There we go. That was interesting. Why was there no interactions? Have I lost my mind on how it works? Oh. Oh, it doesn't break model hierarchy. I forgot about that. Model hierarchy is preserved, and thus we wouldn't be considering interactions until we add in enough variables to get interactions, i.e. we add in total transactions because it's the best. Then we add in the next variable we're adding in is wallet share. We add in wallet share, and all of a sudden now we have an interaction to consider. So once again, we would add in here first purchase because first purchase lowers the AIC the most. And now we've got more interactions to consider, and we are actually now adding in an interaction, which you see right here by the interaction being added. The procedure continues in the search procedure where we keep considering variables to add in. We are considering removing them too because we're going in both directions where we can add variables and remove variables. But the procedure ends when the best option is to do nothing. If you do not have in, like if you have in a variable and you have an interaction, you have to have in both the things. So this model right here has in total transactions and has in total transactions wallet share interaction. So it has the variables and it has the interaction, and that means it preserves model hierarchy. Does that make sense, Brendan? We would say this model preserves model hierarchy. But if you went and had a model where you took this model right here and you removed out wallet share, because you have the interaction term in your model and you do not have x1 and x2, x2 is missing from the model. We're pretending in this moment right here. If you remove out x2, you've broken model hierarchy. It's possible to make a model that has x1, x2 interaction, but because you don't have x2, we would say this does not have model hierarchy. It doesn't matter. I mean, it does. It matters and it doesn't. It's a statistician on a good or bad day, and how they feel about it. That's what would matter right there. Does the statistician care? I don't know. The final model we get is going to be stored into object S. Yeah, it's kind of like, it kind of matters. It's kind of nice. It's nice, but it's not super nice. So this is the final model we have right here. We can actually view it by going here to summary of S. And it explains 96% with a typical miss on the customer lifetime value of 175. This is a very good model. 96% of customer lifetime value with an adjusted R-squared of 95.77, virtually identical. And we see right here 175 is the typical miss on customer lifetime value. Let's take a look at what it looks like just to see if that's kind of big, because cost lifetime value has a range of about $4,000 something. So 175 is a pretty small typical miss. Just kind of getting an idea of units of miss right here, because customer lifetime value has this range, even negative. Interesting. So that's pretty small right there. The formula presented in the last step of the output gives the order in which the variables were added. Good stuff. Which was the variable added to the model during the search, which was added last? Well, we can take a look. The first variable added was total transaction. The last variable added in was the interaction right here with wallet share and last transaction. And we can see that, oops, was that the right? There it is, wallet share last transaction. And that would be the one right there on the last procedure. And we did look at the first. Nope, pretty good stuff, right? So just looking at this right here, total transactions was added first, and wallet share last transactions interaction was added last. Is the model found by the search using the step which includes interactions preferable to the model with the exhaustive enumerated reg subset? which did not include interaction. Why or why not? Okay, so what should we compare with these models? What should we compare to see which model is better? Any idea? Who can help me out? What should we compare with these models? Here it is right here. There it is. What should we compare? AICs, exactly, Brandon. Great job. AICs was 5,185. So search had 5,185, and reg subsets. We got to go find that. Reg subsets. Let me run the search again real quick and see it. Wrong one. There it is. So actually, we could do. No, it shows it right here, anyways. It is. There it is, right there. There's the AIC of the search, and the reg subsets has an AIC of this. And so the answer is, which of these are better? Well, it should be pretty obvious. The search, or the all possible, didn't include interactions because it just would be a quintillion, quadrillion, octillion models. The answer here is pretty obvious, and we were able to find something better with the interactions using the search procedure. Lower is better. So the search procedure did better. Interactions should be included. That's kind of the practical significance of this. Like, why do I care? Well, we were able to find something a good bit better with the search procedure than we were with the reg subsets. So yeah, we should definitely include it. We have seen interpretation of the models with interactions difficult in either implicit regression, blah, 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 blah. Describe the relationship between lifetime value and income, which is involved around the interaction. Oh my gosh. Press enter to get the relevant plots. Okay, we want to look at incomes, interactions. Okay. Let's look at incomes, interactions right here and see what's going on with this variable. Sounds super important. Okay. Graphics. Income with wallet share, right? Was it? Okay, let's take a look. That's a pretty neat interaction right there. The income. Wait, is that income wallet share? What? Something interesting in the moment. Oh my gosh. This is cool. So just to check, will you be... Yep, I'm adding timestamps to this. A few have been added already. Question 1, the step procedure we're currently on. Thank you. Noah, good question right there. If you look at this, this is the reference level of income, black line, and then we are seeing higher levels of income, generally speaking, till we get to the highest level of income. And if you look, the relationship here, so wallet share has a negative relationship to customer lifetime value till you get to the highest level of income. So the relationship wallet share has with customer lifetime value depends on somebody's income level. When someone has a very low level of income, the lower levels, there's a negative relationship. But for higher values of for income, for higher values of income, because this is someone's in the 0 to 30,000 up to the 90,000 to infinity, infinite money right there. We would see that wallet share starts to have an insignificant relationship to the point at which wallet share actually has a positive relationship for the highest levels. The lower levels are having a more negative relationship, gets weaker, but finally passes through to having a positive relationship. And that is how we would describe that right there. And C Interactions has done a good job of explaining that to us. The model selected in the build procedure, though the closest to the truth of the ones considered, may not actually provide a reasonable reflection of reality. We must always check it with the check regression and check the 3 classical conditions. So some really good stuff right here. We love some check regressions. Check regression of our model. Let's check this out right here and see what we got. And we need to first finish this off. There we go. And then we need to run our check regression. Woo! Oh my gosh, that's some heteroscedasticity right there. That is heteroscedastic. Big problem you got right here is there's a lot of points at the start, and then it kind of really fans out. So definitely good evidence of heteroscedasticity. Presence of outliers and non-normality over here. Linearity looks to be the only thing that's good, but we might, who knows, fail some tests right here. I know that normality bad, and the skew right there. We could put the extra equals true on. We have enough to check the plots, which I usually just go to anyways. There's a lot of issues of linearity. Different variables, like this variable has linearity. You can't do it on those. This has linearity. That's fine. Some linearity issues, but I don't see it in the overall plot. The equal spread is super bad, and the normality is super bad. But here's the thing. Let me ask you this. are you still probably going to use this model? And this is the answer to the question. So think this over. Are you still I mean, this model has some problems. It's got a heteroscedastic problem. It does worse on higher values or predicted values. There's more variation. There's some problems with outliers. The normality, it's bad, but it's mostly due to outliers. Like there's that one, then there's those 1, 2, 3, 4, 5. Really those ones there. But overall, do you think you should use this model? Yeah, no model's perfect. Overall, it's like, it's pretty bad on the conditions, but let it pass. We'll say okay. Okay, next question. Here we go. Question 2. Are we doing the build model? So let's see here. Load in the dataset customer acquire. In this dataset, the goal is to describe the relationship between the probability of acquiring a customer who has previously churned after they've gotten a special offer. Let us search for a model, which we've considered all two-way interactions using these variables right here. Remember that you can do all two-way interactions by using the twiddle dot squared. For example, if you fill out, okay, cool. Let's try 2 approaches right now. We have to use the GLM right here to make sure it works because we're doing the reacquire. So this is going to take a moment, not too long. But let's go here and store naive equals GLM. And let me get the reacquired data set, attach, reacquire. How do you spell reacquire? Oh, it's that. I'm cheating by doing this. Oh, we've masked something that means it's already in there. Let me make fonts a little bit bigger, so I'm having a hard time seeing. There we go. I'm looking at the screen, looking down while doing it. Okay, so look over here. One more bigger. Wrong thing. Over here. There we go. Okay, so it wants these variables right here, and it wants all two-way interactions. So we're going to copy these. Ignore those values. That's cool. And we're going to go right here, and the y variable of interest is reacquire, right? Where's reacquire? It is spelled reacquire. There it is. And now we need to include these, and this will help right here with spelling them. And this is interesting. The way you have to do this here, I think a lot of people run into a small problem with. I'll show you the way of doing it. I think this is also in the assignment, so this will make life a little bit easier. Now, and it kind of alludes to it. So we've got all the x's in. Let's make sure our model looks nice and neat. We're not done yet. Data equals cust, there we go. Cust reacquire, and then family equals binomial. We're going to make this look nice and pretty right here in a second. So there's the binomial. You don't need that. There's the data, and then we go right here, and how we make it pretty is we do the following. We say 2 variables go on this line to hang out together. Really? 2 variables go on this line. Yeah, you got to do it after the plus. 2 variables go on this line, 3 variables go on that line. That's good. So these are the x variables right here. And we can make this model. Wait for it, wait for it, wait for it. This is not the model we're making, but this should work. Always test to make sure your stuff works. And then go here and highlight these and put them in parentheses. And then go raise to second. So now we've made not the naive, but the full model. More on the naive in a second. So there's the full model there. There's the naive is just going to be take out all your x's and just put in the 1 right there. So you can see the arguments on the way it works. I don't like, oh, let me re-express these. 2 seconds. Control I fixes the formatting right there. Now it looks a good bit better. You want to make your code look as nice and neat as possible so people can see this is the formula right here, y tilde x, and we have right here y variable, no x's, data frame, and we're doing binomial, which is logistic regression because of categorical y. Next, we go right here in the full model. That's the naive model. We're at the end. Yeah, no worries, Kayla. Yeah, that's what we try to do right here. That's the whole goal, is to be like, okay, y tilde all my x's raised to second, and then we have the data frame, comma, the family binomial. Try to make your code look nice and neat. Really helps. Helps me look at code too. Sometimes I'll be reading through someone have like this code that wraps around the screen like 10 times. I'll be like, because you're still inside of the model specification right here, which is the first argument. That's why it's sub-indents right there. So we make both these models, and it automatically gives us the 2 search procedures. So once again, we're going to make the search procedure look a little nice and neat right here. so we can understand what's going on in the search procedure. The search procedure right here is going to choose the starting model. No worries, just hit enter after some commas and you can make it look a lot nicer, because it's what model are we starting with? What are the bounds by which we're selecting models? The lower is the naive. We can go as low as the naive. We can go as high as the full. What directions are we allowing ourselves to search? And then are we going to watch what happens? And of course, we're going to watch what happens. It's too quick, though. So this is the model it found at the end right here. The final result is the end model, and it only put in lapse and age. So those are the only things it input into the model. But this one right here is a little bit different on Search 2. Search 2 is going to start with the full. So what do you think is the first thing it's going to do? If it starts with the full, it probably would have to do what to start right here? If it starts with the full model, it's going to have to remove stuff. Now, I know it has the option to go both ways to add and remove things, but if you start with everything in the model, you have to move backwards to begin with. This one should hopefully take less than a second to do, or less than half a second. There we go. You kind of got to watch some like numbers fly across the screen pretty quick. But it's going to be removing models. We actually get a different endpoint right here. And the reason this happens is because if you're trying to search for the best possible model, well, one, we're not considering all models. At this point, what we are doing, and we did examples like this in class today. Well, no, we want to go forwards in time. There we go, forwards in time. Oh, but we broke the timeline. So you are trying to figure out where to go, and you're going backwards and forwards. If you start up here, you might end up a different place going backwards. All answers are right. All answers are wrong, Brendan. Different data is going to come to different conclusions, because sometimes you travel backwards and you find a really good place. Sometimes you travel forwards, you find a really good place. You never know what you're going to find when you look for pizza. There's no right answer. No, it's a good question. Let's throw some 500 points out there. Let's throw. I need to make a 1,000-point button. Why do I come up with point buttons and then I break my point scale? I'm like, you know what? We'll do points in intervals of 5, 10. I've got a 5-point button. You never see me press that one. There's 5 points. Oh, that's 10 points. I don't have a 5-point button. I have a 10-point, 20-point, 50-point, 100-point. All I press nowadays is the 100-point button. I've ruined everybody by throwing out 1,000-point stuff. What have I done? There's no right answer to backwards or forwards or both. There's no right answer. All models are wrong. And so what models were found, or what model was found starting with the naive? Let's go check out a summary of it right here. I like to watch the procedure because this is kind of fun. I don't know. I like output. The variables in the naive model were lapse, offset, and age. The variables in the starting with the full model going backwards, or both directions. Both are going in both. One's starting at the naive. How do you know where it starts? It's the first argument. This one starts with the naive and has fences here. It can't go lower than naive. It can't go higher than that. It can go backwards and forwards, go in both directions. This one starts with the full model and allows for both directions and fenced in by the naive and the full. Like, it can't go lower than the naive, which is impossible anyways. You can do things like create a model with 2 variables in it to force those variables in. Does that make sense, everyone here? Brendan, Noah, and Kayla? You could technically make a 2-variable model. And you could start with that 2-variable model and then search using that. And then you can't go lower. But you could start with a 2-variable model and allow it to go lower by using a naive. So that's just like saying you cannot go lower than this model. So you could say, I want those 2 variables in no matter what. I just called 2-variable model like a name. Like, I'm going to start with a 2-variable model, and you can't go lower than that 2-variable model. So that puts a lower fence on it. This would say you can go lower than the 2-variable model. Like, if you want to move out those 2 variables, whatever. But we're starting with those 2 variables in. So that's how it works right there. This is the model you start with, and these are your fences by which you are allowing it to search within. We don't have a 2-variable model. It's just hypothetical in this scenario. The model that is the full model has in a few more. When we started with the full, the off amount, lapse, gender male, age, and an interaction, preserving model hierarchy are with the 2 main effects in there. That's got it. Your boss wants you to choose between these models. Which one do you pick? Ooh. Funnily enough, you can actually go right here and do AIC right here. Hints for the final. Hints for the final right here. I didn't want that one. I mean, it's a little bit of a difference. Which one do you pick? S1 or S2? S1 or S2? Using someone. Which one do you pick? Describe how the probability. Cool. Interpretation coefficient. Careful. There's S1. What do we want with AIC? With AIC, we want what or AIC? With AIC, we want the what is AIC. This is AIC right here. We want the what is AIC. S2, yeah. And I think it comes to the same. Let me look at. Is it doing slightly? Is our AICC? Oh, wait, did I say it was 548 or something? It was. 548? Yeah, it's doing the same. Good, good. And then the first one, and that AIC is that 553. So that should be 553. There it is right there. It's rounding it up. Cool. Should come to the same number. It's using the same procedure, I believe. Some things calculate AIC differently. That drives me nuts. So we would go with, and this one's 548 or something. So we would go with the one that started with the full model. So yeah, full model looks to be the one to go with. Your boss wants, yep, we chose the full model. Or we chose with starting with the full model. So now we need to talk about how lapse works. Okay, so are we predicting somebody's reacquired yes or reacquired no? Are we predicting somebody's reacquired yes or reacquired no? Be careful. Which one of those are we predicting the probability of? Remember, this is logistic. This is good reviews from previous weeks. Are we predicting somebody's reacquired yes or reacquired no? And how do you know logistic, the level of interest? So are we predicting someone is reacquired yes or reacquired no? This is logistic with the level of interest. We'd be predicting someone is reacquired yes or no. Good, quick test questions right here. Now remember, that's a reference level. So in logistic, the level of interest is, does that make sense? In logistic, the level of interest is last. So we are predicting the probability of yes. So all these coefficients right here are designed to talk about the increase or decrease of probability for the level of interest. So does that make sense right there, Brendan? In logistic, the level of interest is last because this is a y variable of interest. And so we are predicting the probability someone is reacquired yes. Reference levels are first. If this was an X, that would be the reference level, which would be no. And then indicator would be yes. So it's kind of the one you always see is like the last alphabetical, whether it be the indicator or whether it be the level of interest. And so we want to look at lapse right here. And so lapse, and just think about logically speaking, where we have two individuals who differ in their amount of time that they've lapsed. The individual who has had a longer lapse would be what likely to reacquire. It has a negative coefficient. It's the most statistically significant out of all of them. And we're talking about how long it's been that someone's contract has been up. So between two individuals who differ in the amount of time they've lapsed by one period of time, whatever this period of time is, whether it be a day, a week, a year, the individuals who have a longer period of lapse and think it's a negative coefficient and we are less likely to be required. Exactly. Remember, we don't mention the value. Like whatever we do, we don't want to say this is like the change in probability because the sigmoidal curve is going down, but it's not constant. It's just that we know two people who differ in the amount of time they've lapsed in their contract. The person who has a longer lapse period is less likely because negative coefficient to be reacquired. Remember, Logistic talks about probabilities. Is this a good? This is a really great assignment. Really great. Because it does the check regression right here and everything. And check it out. Is this model a reasonable reflection of reality? Now I want to do one more part of this. Is this model right here a reasonable? Is it like reasonable? Yes or no? Is this good or bad on this check regression? A lot of review on this. Is that good or bad? Yeah, it's very good. That's awesome. You got two friends here saying use it and use it. High p-value on this means the assumptions are met. The null hypothesis is the assumptions are met. So when you see high p-value here and high p-value here, that's good. Low p-values means there's a problem, like we saw earlier with our search model on the previous one we had some low p-values indicating problems with heteroscale. We even have that on the screen. There were low p-values for equal spread, and there were low p-values. Oh, we got too much search procedure stuff. Oh, yeah, I got a bunch of nonsense on the screen. Oh, there it is right here. There's the equal spread p-value indicating a problem, equal spread, and the normality of residuals also had a problem too. It was pretty bad, but we were like, maybe we'll use it. There's one last thing I would suggest doing with this, and we should see how our model predicts. I want to make sure people have this if you're taking the take home, because how could I look at, last but not least, to see how my model does right here? Don't get confused. Does anyone know the thing I should look at to see how this model predicts at reacquiring people? And high p-values are good on check regression, exactly, because then we don't reject the null that the condition is met. How would I check, how would I look? Now, don't get confused. How would I look at to see how this model's predicting? How would I do that? To say, how's this model predicting? You want to look at a matrix. You want to look at a confusion matrix. And there it is. So we could ask many questions. Question being, how does the naive model predict? Well, luckily, it predicts the same as the level of interest. Most people our company got back, and I'm only looking at this data. The rest of it, it doesn't matter. It does matter when we go inside of it and we talk about the predictions the model makes. If you want to know the accuracy of this model, you have to look at what's called the on-diagonal. The on-diagonal are the things where we predict someone's not reacquired and they're actually not reacquired, and we predict they are reacquired and they actually are reacquired. So this is the amount of people we get correct. And when you divide that by the total amount of people in this data set right here, you will find out the accuracy of the model. Now, it's easy enough to find out the misclassification, because if you find out the accuracy, well, then the misclassification is 1 minus. So now we have the accuracy is about 72.4%, and the misclassification the people will get wrong. And the misclassification I call the off-diagonal, because it's the ones that are mismatched, where you predict you will get somebody and you actually don't. Or you predict you will get somebody, or there it is, predict will get and actually don't. I said that reverse. First one was you predict you do not get them and you actually do get them. But also we should know one more thing, and we talked about the naive model here. When it comes to the naive model and how the naive model makes predictions, the naive model does not have the predictions of the model. So it would not have these predictions inside of here. The naive model only knows the values of y. So the naive model would predict the majority level. Can anyone in the chat for 1,000 points tell me the amount misclassified by the naive model? If the naive model predicts everybody is actually reacquired, the amount misclassified by the naive model would be what? What is the amount misclassified by the naive model? It is what? How many are misclassified? Not 100%. How many are misclassified? Because it says everybody's reacquired. So it would get right the people who are reacquired. So don't worry, I'm throwing 1,000 points out. Don't worry about it. We're just here to practice. It would get right the people who are reacquired, but it'd get wrong the people who are not reacquired. So how many does the naive model get wrong? The naive model's misclassification rate, we only look at that information there. The naive model would get wrong what... that sounds about right. That sounds about right. 41%, 205. Great job. Yeah, that is correct. Doing the math in my head right there. Yep. And does that make sense? It gets wrong 41% because 41% is the minority level. So whatever percent the minority is, it just gets them all wrong because it says, hey, everybody's reacquired because most people are reacquired, but then it gets wrong the people who are not reacquired. Does that make sense right there, Brendan? How it works is it just says most people are this, I guess everybody's this. And then it would get wrong. It would predict the minority are the majority. So it says like most people are reacquired. Well, I guess everyone is. And then it would get those people wrong. It does not have the information on predictions. So you wouldn't have that other information over there. Just a lot of people think, well, what I should look at in here. No, don't look at that. That's the model predictions. This is the information the naive has. Well, great review. Right under an hour stream. Good activity. And if you got questions, let me know. I will see everyone later. Keep up the great work and let me know if you have questions. Bye for now, everyone. Bye.